Okay, we got a problem here, and it's a conservation of momentum problem where we have a situation that two objects are going to collide and you have a before-after. So let's look at it. On the left-hand side of your screen, you see that before the collision, we have a 0.5 kilogram object moving at 10 meters per second to the right, and a stationary yellow 4 kilogram object just sitting still. And that is what's the situation of our system before. After they collide, the 0.5 kilogram white object slows down considerably. It slows down from initially going 10 meters per second. Now, after the collision, it's going 1.1 meters per second. And the question is then, how fast is the yellow 0.4 kilogram object going to be moving? And in what direction? So we solve this type of problem with conservation of linear momentum. And we're going to start out by looking at the before. So what's the momentum of the system before? So the total momentum before is the momentum of the white object, which is 0.5 kilogram times its velocity, which is 10 meters per second. And we have 0.4 kilograms times its velocity, which is 0. I'm going to say let this direction be positive. After the collision, we have the 0.5 kilogram object traveling 1.1 meters per second, and again that is to the right, so that's a positive. And we're going to have the 0.4 kilogram object moving at some velocity v. We're going to add these momentum after, we add the momentum before, and now we're going to set these two quantities equal to each other because momentum is conserved before and after a collision. It's the total momentum that gets conserved, not individual momentum or momenta. In other words, if you look here, before the collision, the white ball or the white object had a momentum of 0.5 times 10, which would be 5 kilogram meter per second. After the collision, we have a smaller momentum. We have a momentum of, what would it be? Half of this. So 0.55 or something like that. Kilogram meter per second. So we've lost momentum here. The white object lost momentum. However, the momentum lost by the white object was picked up and gained by the yellow object. Because initially here the yellow object was still, so it didn't have any momentum. Now it starts to move, so it did pick up some momentum. Where did it pick up the momentum from? Well, the white object lost some. But when you conserve momentum in a system, the total momentum before is equal to the total after. So let's start solving this particular problem then. We got 0.5 times 10, which will give us 5 kilogram meters per second. This here is 0. So that's going to equal this here, which I guess I didn't calculate it out. Whatever that is, let's do so where were we? This is going to be 0.55 kilogram meter per second plus in yellow, mind we'll keep it all in yellow, 0.4 V. So we subtract this off of here. So we're going to get 4.45 is going to be equal to 0.4 V. and then divide both sides by 0.4. So V will finally equal, let's see, 11.1. And it comes out positive, so it's 11.1 meters per second in this positive direction. So we see with this example how we can use conservation of momentum in order to solve these momentum type of problems. Let's just do quickly, see if we could do another problem. I'm going to wing this because I didn't prepare it, but anyway, hopefully it'll work. We have two skaters. Here we go. One guy here on skates and another person here on skates, and they're at rest. And then the question is, that's your before, and then after they're going to push apart, and this guy is going to go that way, and this person here is going to go in this direction because they're going to push apart. They're on roller skates. Let's say this this guy here is 50 kilograms. This guy here is let's say 75 kilograms, and they're going to push apart here. So the 50 kilogram guy is here, the 75 kilogram person is here. And let's give some speeds here. We don't know. Let's say this guy's going off at 2 meters per second. So the question is, what is the velocity of this guy over here? Well, it's a total conservation of momentum principle. This is the before scenario. This is the after scenario. What's the total momentum of the system before? Well, if they're both still, the momentum of the system has to be 0, because we've got the 50 kilogram guy times a 0 velocity plus the 75 kilogram guy times a 0 velocity. This whole thing is 0. So the total momentum before is 0. That means that the total momentum after has to be 0. So what's the total momentum after? Well, we've got 50 kilograms of this guy going in the negative direction, so that's going to be -2. Plus, we've got the 75 kilogram guy, and we don't know what the velocity is. All right? But we know that this plus this has to be 0. The total momentum has to be 0 after, because it was 0 before. So if we set this whole thing here equal to 0, we're going to find that we're going to have negative 100 plus 75V equals to 0 because it was 0 before. So 75V equals 100. So V is 100 divided by 75 meters per second, and this is going to be plus. So that's how we do this, and we just found out now what the 75 kilogram person's velocity is going to be after they push apart. So I hope that helped. That was just 2 examples of conservation of momentum. You simply take the mass times velocity of each object, considering that velocity does have a direction. You add up the totals before, the totals after, and you set them equal, because the total momentum of the system now before equals the total momentum of the system after. Individual objects' momentum, that can change, but the total of the system stays constant, and that's what I need you to know.